All right. Now we're done with precipitation reactions and we can go on to acid-base reactions. Acids, according to the Arrhenius definition, are substances that increase the concentration of hydrogen when dissolved in water. The concentration of H pluses when dissolved in water. That's the Arrhenius definition. The Bronsted-Lowry definition is a proton donor. That may seem strange, but if you think about it, hydrogen has an atomic number of 1, meaning it has 1 proton. Its mass is also just 1 because it doesn't have a neutron. And so if you have a hydrogen atom that has lost an electron, it's simply just a proton. So H pluses, protons, same thing. So Arrhenius says an acid is a substance that increases the concentration of H plus, and Bronsted-Lowry says that an acid is something that donates protons in a solution. And then there's the Grammont definition, and that is that acids start with an H. All right, there are 7 strong acids, as you know: hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, chloric, and perchloric. They're strong acids because they dissociate completely in water. Now, we can group them into categories based on the number of H pluses or protons that they donate to the solution. Monoprotic acids produce 1 hydrogen when they are dissolved in water, like HCl or HNO3. Hydrochloric or nitric are both monoprotic. In this case, it's a strong electrolyte, a strong acid. This is one of our strong acids. Now, diprotic acids produce 2 H pluses when dissolved in water. Examples of that would be the strong acid H2SO4, sulfuric acid, and then triprotic acids. Those produce 3 hydrogens when dissolved in water. So phosphoric is an example of a triprotic acid, but it is not a weak acid or a weak electrolyte because it does not dissociate completely in water, hence the 2 arrows going each direction. All right, bases, substances that increase the concentration of hydroxide ions when dissolved in water. That's the Arrhenius definition. And then the Bronsted-Lowry definition is that bases are proton acceptors. So if you think about it, a hydrogen H plus ion is simply a proton. Well, bases accept that proton. The hydroxide in bases will accept that proton, and so you'll have H combining with OH, so then you've got yourself a water, which is always a product of an acid-base reaction. The Bronsted-Lowry definition, with it being a proton acceptor, it's a broader definition. It's kind of a grammatism to say that bases end in OH, because that's certainly not true of all bases. Baking soda is a weak base. It's sodium hydrogen carbonate. It doesn't have hydroxide in it, but it does accept protons in acid-base reactions, so it is a base. All right, the strong bases are the soluble hydroxides. Anything with a group 1 metal and a hydroxide is soluble, so that's a strong base. And then we have the bottom of group 2, calcium, strontium, and barium. Hydroxides are also strong bases. So this is the kind of thing you'll have to do to start, and that is just deciding whether a substance is a strong electrolyte, a weak electrolyte, or a non-electrolyte. Okay, we have calcium chloride. Okay, that's ionic, so we have to ask ourselves, is it soluble? And according to our solubility rules, halogen ionic compounds are soluble except for those with silver, mercury, or lead. So calcium chloride is soluble. HNO3, well, it starts with H, so it's an acid. It is nitric acid. That is one of our strong electrolytes. So it's soluble, of course, in a strong electrolyte. Ooh, going back to the calcium chloride, I just said it was soluble, but because it's ionic, it just is, and soluble, then it is a strong electrolyte. Nitric, being a strong acid, is a strong electrolyte. And then we have ethanol, which is just a bunch of C's, H's, and O's. It's just there's no metals in it, so it is simply a covalent molecular compound. It's actually an organic alcohol. So that would make it a non-electrolyte. Molecular compounds do not conduct electricity when dissolved in water. Now we have formic acid. It's an acid. It says so in the name. And it starts with H. That's another clue. And it is not one of our 7 strong ones, so it is a weak acid and therefore weak electrolyte. And then lastly, KOH. That is a hydroxide, and it's soluble because potassium is in group 1. So it's a soluble hydroxide, and therefore a strong base, and therefore a strong electrolyte. All right, that's the book explanation. I like mine better. All right, let's see. Now this one, we have to think about concentration. Consider solutions in which 0.1 moles of each is dissolved in a liter of water. We have calcium nitrate, glucose, sodium acetate, and acetic acid. Rank them in order of increasing electrical conductivity. Based on the fact, and this is important, that the greater the number of ions in solution, the greater the conductivity. So who's going to be the weakest here? Which one is going to be, I guess, the worst at conducting electricity? Well, it's not going to be either of these ionic compounds, the calcium or the sodium ones. That's an acid, but it's not a strong one, so we know it's going to be in the weak category. And then that leaves glucose. Glucose is just C's, H's, and O's. That's just an organic compound. It's a molecular covalent compound. So when it dissolves in water, it's not going to produce ions at all, and therefore will be a non-electrolyte. So glucose is the lowest in electrical conductivity, being 0. Next up is going to be our weak acid, the acetic acid. And then we have the 2 ionic compounds. The calcium nitrate, being a nitrate, is soluble, so it's a strong electrolyte. And the sodium acetate, being that it's got sodium, a group 1 metal in it, it's soluble, so it's a strong electrolyte. So how do you figure out who the winner is? Well, you have to look at the number of ions that are formed when it dissolves. The sodium and the acetate, when it dissolves, it just makes 1 sodium ion and 1 acetate ion, for a total of just 2 ions. But now when you look at the calcium nitrate, when it dissolves, you get 1 calcium and 2 nitrate ions, for a total of 3 ions. So the calcium nitrate will have the greatest electrical conductivity. So the lowest electrical activity goes to, or conductivity, goes to glucose. Then the weak acid, acetic acid, would be a little conductive. Then the sodium acetate would be very conductive, but calcium nitrate would be even more so because there's more ions. All right, so acids and bases, neutralize each other, so they're called neutralization reactions. Whenever you mix together an acid and a base, you get a salt and water, and sometimes gas bubbles. So acid-base reactions, the acid donates a proton. So this is how ammonium hydroxide is formed from ammonia gas. You can see here what's happening. Okay, we end up taking an AH off of the water, giving it to the ammonia, making it ammonium, an H4+, and now the water is just an OH. Now we've got ourselves a strong base. So in this instance, the ammonia and the water were able to do an acid-base reaction. So who's the acid here? Well, if acids are a proton donor, in this case, that H+ proton was donated by the water. So here water acted like a base. And the NH3, I'm sorry, I didn't mean to say base, I meant to say acid. Here the water acted like an acid and donated an H+ to the base ammonia, NH3. NH3 accepted that proton, that H+, and in doing so was a base. So not your typical acid-base reaction, but nonetheless an acid-base reaction. All right, so generally when solutions of an acid and a base are combined, the products are going to be some kind of salt, not always table salt, but some kind of salt, and water. Notice the states are a little different. We start out with two aqueous things, but unlike a precipitation reaction, we don't form a solid, we just form the liquid water. So we still have a soluble salt floating around in the water, but we have liquid water as a product. So there's the complete ionic equation. Once again, you bust up all your strong electrolytes. Stop that. Computer's being weird. You bust up all your strong electrolytes into ions. So the HCl and the sodium hydroxide get split up. And then in the products, we have the salt split up. We leave the water together. Covalent compounds like water and carbon dioxide and ammonia and H3, you don't bust those up into ions because, well, they're not ionic. They're covalent. So they don't split apart into two separate ions. So we leave it written as liquid water. That's for the complete ionic equation. Now, for the net ionic equation, same rule as with the precipitation reaction. You cancel out the spectator ions. You cancel out the ions that have not changed in terms of their state or their charge. They haven't done anything but floated around in the water. And in this case, the sodium and the chlorine are still floating around in the water being aqueous after the reaction. So in a strong acid and strong base reaction like this, you're always going to get the same thing for the net ionic equation. You're going to have H plus and OH making water. This goes for whenever you have a strong acid, one of those 7 strong acids, or a soluble hydroxide, a strong base. You're just going to end up with H and OH making liquid water in your net ionic equation. Now that's not true for weak acids or weak bases, but for strong acids and strong bases, your net is always going to look the same. Now, a reaction between milk of magnesia, which is MOMS, that stomach medicine, MgOH2, magnesium hydroxide, that's a base, and hydrochloric acid. Now, is magnesium hydroxide considered a strong base for us? Nope. It is in group 2, but it's not at the bottom of group 2. It's got to be calcium, strontium, or barium to be soluble. And so it isn't soluble. So it's not a strong base. So this is a weak base and a strong acid example. Oh, okay. So in this case, you won't simply have H plus OH making water. This is one I'll just have to work out in class. All right, another type that can happen is your base can be a carbonate, like baking soda or chalk, sodium carbonate, calcium carbonate. So if you put an acid on a carbonate, you're still going to get salt and water, but you get a little something extra, you get CO2 bubbles. And that's what's happening here. All right, so these are considered gas-forming reactions. They're still metathesis or double replacement. Just the products aren't as you would expect. You don't just get salt and water. You also get the carbonate gas. Now, it can also occur with the sulfate, so you can get SO2 instead of CO2. All right, so here is chalk, calcium carbonate. Chalk does not dissolve in water, so notice it has a solid written next to it instead of AQ. And then there's your strong acid. You get salt and water, but you also get CO2 gas. So in terms of who's changing here in a net ionic equation, everything's changing, almost. Okay. Well, actually, yeah, everything is changing. The calcium went from solid to aqueous. The carbonate went from solid to some of it being a gas, and then the other O is in the liquid water. And then one thing didn't change. The hydrochloric, the H went from aqueous to now being in liquid water. The Cl is the one spectator. It was aqueous to begin with, and it still is in the product. So, while writing the net for this, the only thing you could leave out was the Cl negative. And then when you would write the complete ionic equation for this, Don't bust up the calcium carbonate into two separate ions in the net ionic equation or the complete ionic equation, because it does not dissolve in water. You would leave the calcium carbonate and the CO2 molecular compound and the molecular water compound. You would leave all those together.